In Chapter 4, we discuss covalent bonding and simple molecular compounds. To begin with, we're going to talk about covalent bonds, which is an alternative way that atoms can be bound to one another compared to ionic bonding. So in the early 20th century, the American chemist G.N. Lewis devised a model of bonding in chemical compounds. And the first point that he made was that valence electrons, those in the outermost shell, are the most important in chemical bonding. And then he said that valence electrons are transferred between dissimilar elements, namely metals and nonmetals, to form ionic bonds, but they are shared between similar nonmetal elements to form covalent bonds. And it's this sharing of electrons between similar nonmetal elements that we're going to be discussing in this section. Whatever the type of bonding is occurring, G.N. Lewis said that when electrons are shared or transferred, the intention is that the atoms gain a complete octet. And there's only one real exception to this rule, and that is hydrogen, and hydrogen is happy to obtain a duet with 2 electrons because its nearest noble gas is helium. So it's important to recognize that atoms form covalent bonds by sharing electrons with each other. So if we think about 2 hydrogen atoms that are separated by a large distance, they each have 1 electron in a 1s orbital. And if we bring these atoms together so that these 2 regions of space that the electrons occupy overlap, what we find happens is that the electrons take up a position exactly halfway between each nucleus. And by doing this, each nucleus feels an inwards attraction towards these 2 shared electrons, and that holds the atoms together to form an H2 molecule. And if you recall, hydrogen is always found as H2 molecules rather than individual atoms. So we can use Lewis symbols to represent the formation of the covalent bond in the H2 molecule. So here's our first hydrogen atom, here's our second one, and now they come together and they share their 1 valence electron. It's really common that chemists will use a dash, a solid line, between the 2 atoms that are connected via a covalent bond. So one line like this equals 2 shared electrons. So the dash represents a pair of electrons, so that's 2 of electrons being shared by both nuclei. And by doing this, both of the hydrogen atoms obtain a duet. So these electrons that are being shared by the atoms are known as the bonding electrons because they help hold the atoms together. So why does this work? Well, when these atoms come together, there will be a variety of forces. What's holding the molecule together is the attraction of the electrons by both nuclei. However, it's important to recognize that the 2 negatively charged electrons will repel one another. That will destabilize the molecule, and also that the 2 positively charged nuclei will repel one another, and that it will also destabilize the molecule. However, because this attraction is larger than the repulsions, the 2 atoms will stay together. We can also use Lewis diagrams to represent the formation of a covalent bond between fluorine atoms. So here we have 2 fluorines, fluorines in group 7A, so they have 7 valence electrons each. When these guys come together, the electrons that I've circled there will pair up and they will become shared between the 2 fluorine atoms. So around each fluorine there will be 6 electrons that are not being shared, but then another 2 electrons that are being shared. So each fluorine contributes 1 valence electron to form a covalent bond, and that results in each fluorine atom obtaining an octet with 8 electrons in total. And it's important to realize that each fluorine atom has 6 electrons that are not participating in forming the covalent bond, And these are called non-bonding pairs of electrons, or sometimes they're called lone pairs of electrons. So in this case, each fluorine has 3 lone pairs. Now, the 2 examples that we've seen so far involved identical atoms, but it doesn't have to be identical atoms. For example, we could pair up a hydrogen atom with a fluorine atom, and you can see that by sharing the 1 electron on each atom that isn't paired up with another electron, we can form a covalent bond between the 2 atoms. Hydrogen gets a duet, fluorine gets an octet as a result of sharing these electrons, and the shared electrons we can represent by a line, and the electrons that are not being shared we can represent as dots, and that makes it really clear what are the electrons helping hold the molecule together, and what are the electrons that are just sitting on a single atom. So yeah, it's really cool, right? Now notice in here that hydrogen has no non-bonding pairs of electron, but fluorine does. And that is the case that hydrogen will always have no non-bonding pairs of electrons. So we observe that covalent bonding occurs between non-metals. When a group of non-metals are covalently bound together to form an uncharged species, the species that is formed is referred to as being a molecule. A classic example would be water or CO2 or NO2. Now it's also possible for non-metals to covalently bond together to form a charged species. And when they do, that species is called a polyatomic ion. So examples would be the ammonium ion, the carbonate ion, the sulfate anion, the nitrate anion, or the nitrite anion. We should recognize that the atoms that are in molecules or polyatomic ions are chemically bound together, and so as a result they cannot be separated by physical means. What different compounds represent are different ratios of atoms chemically bound together. So for example, water and hydrogen peroxide are both composed of hydrogen and oxygen. However, they have a different ratio of the atom types, so therefore their physical and chemical properties are unique. Water, it's important to drink water. Hydrogen peroxide, if you were to drink pure hydrogen peroxide, you would blister your mouth, and if you drank sufficient, you would probably die. So perhaps we can contrast ionic compounds and molecular compounds in terms of some of their bonding patterns and also in terms of some of their physical properties. So ionic compounds contain elements that are very different from one another, elements that are on the complete different sides of the periodic tables. Most commonly it's a metal with a non-metal. And what holds these guys together is the attraction between oppositely charged ions, the attraction between cations and anions. Ionic compounds are found as crystals. This is an approximately infinite array of cations and anions, just kind of repeating again and again and again and again, billions upon billions of times. There are no molecules in ionic compounds. And all ionic compounds are solids at room temperature. They're characterized by having very high melting points. In contrast, molecular, or sometimes referred to as covalent compounds, are formed between similar non-metal elements. That is, the elements that are in the compound are close to one another on the periodic table. We'll see some molecules are actually formed by elements of the same type. What holds the atoms in molecules together and in molecular compounds together are shared electrons and the attraction of the nuclei of the atoms to those shared electrons. The building block of molecular compounds is the molecule, a small, discrete bundle of atoms that acts as an independent unit, acts independently of all other molecules. And molecular compounds show a greater diversity in their melting points and boiling points, and they can be solids, liquids, or gases at room temperature. So this is an exercise from the book. It says, draw the Lewis diagram for each compound. It says a molecule composed of one chlorine atom and one fluorine atom. So what we're going to do is we're going to draw the Lewis symbol for chlorine. And because chlorine is in group 7A of the periodic table, we know that it has 7 dots around it. Similarly, fluorine is also in group 7A of the periodic table, so its Lewis symbol has 7 dots around it. And I hope you can see that by sharing these unpaired dots, we can form a ClF molecule where both the chlorine and the fluorine have a complete octet with 8 electrons around them. And I've illustrated that 2 of the electrons are being shared by drawing them in as a line. So I'm quite happy with that. I'll just check that everything's got an octet. 2, 4, 6, 8. 2, 4, 6, 8. Everything looks good. Let's move on to the next one. So it says a molecule composed of one hydrogen atom. So hydrogen's in group 1A, gets 1 dot. And 1 iodine. And iodine is in group 7A, so it gets 7 dots around it. And again, hopefully you can see that by pairing up these unpaired dots, hydrogen will get a duet, which is its preferred electron arrangement, and iodine will get an octet. So hydrogen has a share of 2 electrons because it's sharing those that are in the bond, and then iodine has 1, 2, 3 lone pairs, and then 2 electrons that are shared, giving it an octet. Now, all of the examples that we've seen so far involve only 2 atoms, but we can go to larger collections of atoms and form larger molecules. So, for example, a water molecule forms through the combination of an oxygen atom with 2 hydrogen atoms. Oxygen's in group 6A, that's why we have 6 dots around the symbol for oxygen there. So, in a water molecule, the hydrogen atoms are attached to the oxygen through the sharing of 1 pair of electrons, and then the oxygen atom has 2 lone pairs. We can also show how ammonia is formed. Ammonia is formed through the combination of 1 nitrogen atom with 3 hydrogen atoms. Nitrogen is in group 5A, so it has 5 dots around its Lewis symbol. 3 of them are unpaired. The 3 unpaired dots in the nitrogen Lewis symbol can combine with 3 hydrogen atoms to form an NH3 molecule. And this really kind of shows the value of indicating shared pairs with lines, because it looks really crowded around here, but we can see that each hydrogen atom is attached via 1 shared pair of electrons, what we call a single covalent bond, and then there is a lone pair of electrons on the nitrogen. So in this way, the nitrogen gets an octet and each hydrogen gets a duet. Okay. Or we can also look at the combination of carbon with 4 hydrogens. You can see carbon in group 4A has 4 dots around its Lewis symbol. All of these dots are unpaired, ready to pair up with a single electron on each of the 4 hydrogens. So this gives carbon a complete octet with 8 electrons, and each hydrogen gets a duet. In this case, none of the atoms end up with a lone pair. So when we look at the Lewis symbol of the non-metals, what we observe fairly quickly is that the group number corresponds to the number of dots around an atom symbol, and also that the number of unpaired dots in an atom's Lewis symbol indicates what we call the number of octet vacancies, and that is the number of bonds that it tends to form. So carbon likes to form 4 bonds, nitrogen and phosphorus, they like to form 3 bonds, oxygen, sulfur, and selenium. Oh, wrong one there. Oxygen, sulfur, and selenium like to form 2 bonds, and fluorine, chlorine, bromine, and iodine, they all like to form 1 bond. Now, occasionally we do see exceptions to these rules, but they are the general patterns. I've already mentioned this term. When 2 atoms share 2 electrons, we form what is referred to as a single bond. But atoms can also share 4 electrons to form double bonds, or 6 electrons to form a triple bond. And it's important to recognize that the more electrons that are being shared, the stronger the bond is. So in a water molecule, we have just single bonds with 2 electrons being shared. But in an oxygen molecule, we have 4 electrons being shared, and in an N2 molecule, we have 6 electrons being shared, with there being a triple bond between the nitrogen atoms. So it might not immediately be obvious, but in order to form either a double or a triple bond, an atom must have 2 or more octet vacancies. So what that means is that those elements that are in group 7A that have just the 1 octet vacancy, we wouldn't expect those guys to form double or triple bonds. We also wouldn't expect hydrogen, which has just the 1 octet vacancy, to form double or triple bonds either. However, if we go to group 6A, the elements that are in group 6A have 2 octet vacancies. So this means that typical bonding patterns we might see for these guys would be 2 single bonds, or or 1 double bond. When we go to group 5A, we see that these guys have 3 octet vacancies. So typical bonding patterns that we might expect would be 3 single bonds, a double bond, and 1 single bond, or alternatively just the 1 triple bond. So as we move to lower group numbers, we're getting greater diversity in the bonding patterns that are possible. The nonmetal that's in group 4A is carbon, and carbon has 4 octet vacancies. So this gives rise to quite a variety of possible bonding patterns. Carbon will typically form 4 single bonds, or 1 double bond and 2 single bonds, or 1 triple bond and 3 single bonds, or 2 double bonds. So what you see is, of all of the nonmetals, carbon is the most versatile with respect to the bonding patterns that it can form. And it's for this reason that we have a whole discipline called organic chemistry, which is the chemistry of carbon-containing compounds. So there are approximately 200 million known carbon-containing compounds, and all life form on our planet is carbon-based. And really that's just because carbon is the most versatile of the non-metals. It can have the greatest variety in its bonding patterns. In all of the bonds that we've considered so far, each atom has contributed an equal number of electrons to forming the bond. In most of our examples, we had each atom contributing 1 electron and forming a single bond. However, it doesn't always have to be like this. It is most of the time, but it doesn't always have to be like this. So what we've seen so far is that we have one electron on each of two atoms coming together and becoming shared between two atoms, forming a covalent single bond. And that is the most common type of bonding. But there's no reason why one of the atoms couldn't donate both of the electrons or contribute both of the electrons to the pair of electrons that is being shared. And this does happen, it just doesn't happen that often. And when it does, we say that what we formed is a coordinate covalent single bond. So here's an example. This is an acid, HOClO. It definitely exists. And what happens when this compound forms is the chlorine contributes both of the electrons that end up being shared between the oxygen and the chlorine. So something that's unusual about this molecule is that we can see that chlorine here is forming two bonds, which is not what we would expect on the basis of its Lewis symbol, because on its Lewis symbol it only has one unpaired dot because it's in group 7A. And this is kind of typical to see unusual bonding patterns when we have a coordinate covalent bond. So we normally see a deviation from the expected bonding pattern when a coordinate covalent bond forms, and that can be an indication as to what is going on. Okay, so this is another exercise from the book. It says, examine the Lewis structure of NCl3 below. And here's the Lewis structure. It says, count the number of bonds formed by each element based on the element's location in the periodic table. Does it correspond to the expected number of bonds suggested in the periodic table? Does the Lewis structure below follow the octet rule? So let's do the first part and see how many bonds we would expect chlorine to form. So chlorine, if we look on the periodic table, is in group 7A. Here it is. So it has 7 dots around it, and one of those dots is unpaired. So we expect chlorine to form one bond, and it does in each case in this structure. Now, if we look where nitrogen is, we see it's in group 5A, so that means that it's going to have 5 dots around it, and we can see that we have 3 unpaired dots, so we expect nitrogen to form 3 bonds. And 1, 2, 3 bonds, it does. So based on the element's location in the periodic table, does it correspond to the expected number of bonds suggested in the periodic table? And the answer is yes. All right. Now, what we're asked to answer is, does the Lewis structure below follow the octet rule? So we have nitrogen with a lone pair and then 3 shared pairs of electrons. So yes, nitrogen follows the octet rule. And then every chlorine atom has 3 lone pairs and then 1 shared pair of electrons. So if you add all of that up, 2, 4, 6, 8, yes, every chlorine atom follows the octet rule. So the nitrogen follows the octet rule, and so does every chlorine. So the answer again is yes. Okay, so that concludes the section on covalent bonds.